Lecture 2.5, Special Relativity and Time Dilation. In the late 1800s, Maxwell used the electromagnetic equations to show that light is an electromagnetic wave, and he also showed that the speed of that wave is a constant. The Michelson-Morley experiment suggested that light does not travel through a medium, and which was called the ether at the time. And so the question is, well, if the speed of light is a constant, what is that speed relative to? It doesn't appear to be the ether. Now, it's not clear if Einstein was aware of the results of the Michelson-Morley experiment, but he was aware of other paradoxes that were present in electromagnetism. So in thinking about the nature of light as an electromagnetic wave, he proposed two postulates. The first is the principle of relativity that was proposed by Galileo hundreds of years ago, which says that the laws of physics are the same in all inertial reference frames. The second postulate is that the speed of light in free space has the same value c in all inertial reference frames. Another way of saying this is that when asking the question, what is the speed of light relative to? The answer is everything. So everything and everyone in the universe all sees the speed of light in a vacuum as that same value c. So it's sometimes difficult to appreciate just how revolutionary that assumption is. So let's think about how impossible this seems. So let's imagine a little experiment here, a little thought experiment. So we have somebody here with a light source, and we're going to measure the velocity of the light wave by putting two photodetectors on the ground and timing how long it takes to go from one to the other. So there it hit the first one. Now it hit the second one. We can read off the time on our clock. We know the distance between them. And so the speed of light in the ground frame of reference is just the distance between the sensors divided by the time it takes. We're going to repeat this experiment now from two reference frames. So we're now going to add a UFO here, and it's going to have the same two photodetectors on the bottom of the UFO, and the alien here is going to also measure the speed of light. So it's also going to be timed so that as the alien is moving to the right, this back photodetector is going to line up exactly with this photodetector on the ground right as the light beam arrives. So here comes the light. Both the first ones are detected, now the ground, now the UFO. So you can see that, hopefully you could see that, the light moved from here to here for the ground, but it moved from here all the way over to here someplace before that second detector on the UFO found it. So in the alien's frame of reference, the distance between the two photodetectors is the same as what we measure on the ground. So L0 is going to be the same in both cases, but hopefully you could see that it took much longer for the light beam to go from that first detector to the second one in the alien's frame of reference. And that's because, the UFO is actually moving away from the light, and it takes a while for the light to catch up to that second detector. So because the time that elapsed in the UFO's frame, this delta t is much larger than the time measured on the ground, that means that the speed of light as measured by the UFO should be smaller than the speed that we see on the ground, in agreement with Galilean relativity. So that's what we would expect. Just a quick note, we're going to be using this word thought experiment quite a bit. It's a technique that lots of physicists have employed. Galileo was known to use them, and Einstein is also famous for using thought experiments. A thought experiment is just basically a logical argument. You kind of imagine the implications, the logical implications of a set of assumptions, and you see if the results are logically consistent with a theory. So you don't have to do any experiments, you're just looking for logical consistencies within a given theory. So a light clock is an example of a thought experiment. And we're going to use this to derive the equations for time dilation and special relativity. So the way this works is a light clock is basically designed so you've got a perfectly flat mirror up here and then one down here, and you're trapping a light beam. It's perfectly reflective, so we're going to trap a light beam bouncing back and forth between these two flat mirrors. So every time the light beam gets up to the top, it's one tick of our light clock. And this light clock has been calibrated so that every time our light beam reaches the top, then one tick is evolved. So right there is like 3 ticks of the clock, and then so on. So the duration of one tick is just the total distance traveled between going from the top down to the bottom and then back up to the top again. So that's going to be 2L0 divided by the speed of light c. That gives you the time for one tick. Okay, so now, just like before, we're going to imagine a light clock in a moving frame of reference. So we'll have this light clock here, but now the second light clock is going to be moving through space with a fixed speed to the right. And so in order for the light beam to stay trapped between the two moving mirrors, it's going to have a horizontal velocity component, which is going to take it on this zigzagged course through space. So the point here is that if everyone sees the speed of light as the same value, then it means that the velocity of the light beam as it's going along the diagonal here has got to have the exact same value as this light beam going back and forth. But since the velocity is now angled through space, the y component of the light's velocity must be less than what it is when the light is just being directed downward. So since the y component of the velocity is less in this case, it's going to appear to take longer to bounce back and forth between the two mirrors. So let's analyze this. So we're going to start with our light clock at rest. So again, delta t naught, that's going to be the time it takes for one tick, for the light to go down, bounce, and then back up. Delta t is going to be the time for one tick of the light clock that is in relative motion to us. So it's going to be the time from our reference frame for the light to take this diagonal path, go down, hit the bottom mirror, and then back up to the top mirror. Okay, so that's delta t. And what we want to do is find a relationship between delta t naught and delta t. So what we're going to do is start with constructing a right triangle here. So the vertical edge of the triangle is just the distance between the two mirrors, L naught. The horizontal distance is, well, let's see here. The time it takes the light clock to move from here to there is delta t. So the time it takes to go from here to the halfway point where the light ray hits it is going to be delta t over 2. And we're assuming that this light clock is moving to the right with some velocity v. So v times delta t over 2 is going to be this distance that the light clock travels. And now let's look at the hypotenuse here is going to be the distance the light beam travels in half a tick of our clock. So we can get that from the Pythagorean theorem. It's just equal to d squared is just L naught squared plus this quantity squared. That's this. The duration for one tick on our light clock is the time the light beam takes to go from here down to the bottom and then back up. So that is just going to be this total distance, which is 2d, divided by the speed of the light wave, c. So we take d times it by 2 over c, so you get 2 over c out in front. We're going to use this expression up here and replace L naught with c delta t over 2. So we're just going to use this to get rid of the L naught and replace it with c delta t over 2. This is the same expression we had on the last page. We're just basically what we want to do at this point is we want to write delta t in terms of delta t naught, but unfortunately we have a delta t over on the right hand side, so we got to get the delta t's together. So if you square both sides, you get this. Multiply the 2 squared over c squared. Here, the 2 squared cancels that 2 squared. The c squared cancels that c squared. You're left over with this delta t naught. We still have a delta t squared over there. So we're going to move this to the other side of the equation, factor out the v squared, factor out the delta t squared, and you get a 1 minus v squared left over. That's equal to this delta t naught squared. And then we're going to divide both sides by the term in parentheses and take the square root. So we get delta t is delta t naught over the square root of 1 minus v squared over c squared. This is the expression for time dilation. So let's summarize this result. This is the expression that we just derived with simple geometry. Okay, so we need to define the terms and make sure we're clear about them. So delta t naught is called the proper time, and it is the time elapsed on your clock where your clock is at rest with respect to you. So it's your own personal time. Delta t is the time elapsed on someone's clock that you see moving relative to you, and v is that relative velocity. So we'll talk a little bit about the exact how to define delta t versus delta t naught, because it can get confusing at times. Frequently, this expression is written in a simpler form. It's written as delta t equals gamma delta t naught, where we introduce this gamma factor as 1 over the square root of 1 minus v squared over c squared. So this is dimensionless. It doesn't have units. It's just a number, but it depends on the velocity. So when velocity goes to 0, gamma is just 1. As velocity gets bigger, this thing diverges to infinity. In fact, we can see that on the next page. So here's a little tabulation of different velocities expressed in terms of the speed of light. So here's 1% the speed of light, 1% the speed of light, 10%, 90%, 99.99%. And here's that gamma factor. So when you're moving very slowly, the gamma factor is very close to 1. But then as you get closer and closer to the speed of light, this gamma factor just diverges to infinity. It just blows up. While we're at it, it's just good to note that sometimes people define another dimensionless quantity called the beta factor. So beta is just the ratio of the velocity to the speed of light. So before we were writing that the velocity was, say, 0.01 c, well, you could just say that beta is equal to 0.01. So same thing. Sometimes it just makes the math a little bit simpler if you use beta instead of e's over c's. So the gamma, you can write the gamma factor in terms of beta as just 1 over the square root of 1 minus beta squared. And now we can have exactly the same plot, but now plotting gamma as a function of beta. So again, gamma is the amount of time dilation. Beta is a measure of the speed relative to the speed of light. Okay, let's look at a simple example. Olivia speeds by Oscar at half the speed of light, which, as we've just seen, has a gamma factor of 1.16. How long will Oscar have to wait to see Olivia's clock advance by 1 hour? That's kind of worded weirdly. All right, so there's Oscar, there's Olivia. The drawing is from Oscar's frame of reference. So it's usually a good idea, like when you're making a drawing, to try to figure things out. Always be aware of whose frame of reference it's from. Oscar is standing still, so it's Oscar's frame of reference. The events that we're interested in measuring, however, are on Olivia's clock, right? We want to know how much time elapses, as seen by Oscar, on Olivia's clock. So these green ticks correspond to successive events, or ticks, on Olivia's clock. So the proper time, delta t naught, is the time that's measured in a reference frame that is at rest with respect to the events that are unfolding, right? And so since these events are moving in space from Oscar's point of view, it's clear that Oscar is not measuring the proper time. He's going to be measuring the time-dilated time. Olivia, however, is at rest with respect to those events. Like the clock is moving with her, so every tick of the clock is at the exact same spatial coordinates in her moving reference frame. So she measures the proper time. Delta T is measured by Oscar. So then you just, once you figure that out, you've done all the work, right? Then you just like use the time dilation equation and plug in the values. So we know that gamma is 1.16. If delta T naught is 1 hour that elapsed on Olivia's clock, so 60 minutes times 1.16 is about 70 minutes. So Oscar would have to wait 70 minutes for 1 hour to evolve on her clock. I want to point out that the result here depends only on the relative motion of the observers. No one's in a special frame of reference here. So even though Oscar's standing on the ground and Olivia's driving by, you can reverse their roles. So, for example, how long will Olivia have to wait to see Oscar's clock advance by 1 hour? So we're reversing it now. We're now asking Olivia's perspective about Oscar's clock instead of the other way around. The picture is still drawn from Oscar's perspective, which is fine, but the events are now going to be on Oscar's clock instead of Olivia's clock. So we're asking how long Olivia's going to have to wait for Oscar's clock to go, to record 1 hour. So Oscar's at rest with respect to the events. He measures the proper time now instead of Olivia. Now Olivia measures the time-dilated time, get the same equation, you get the exact same result, but now Olivia is saying that she has to wait 70 minutes for 1 hour to tick by on Oscar's clock. So they each see exactly the same thing in agreement with Einstein's first postulate. All inertial reference frames are equivalent. Okay? So they each think that the other person's clock is running slow. Okay, so a final comment on this stuff is the low velocity limit of the time dilation factor. So when the velocity is much less than the speed of light, this gamma factor gets like really, really close to 1. So we can use a Taylor series expansion, this 1 minus x to the nth is approximately 1 minus nx, to show that the gamma factor is about 1 plus 1/2 v squared over c squared when v is much less than c. It's a simple homework problem. If you plotted this alongside of gamma, you can see that the blue curve is gamma, the dashed red curve is this approximation, and so for velocities that are less than the speed of light, it looks like the two curves match up pretty well. Once you get close to the speed of light, like 50% or even closer to the speed of light, the curves radically diverge, right? The blue one diverges to infinity. So anyway, you have another homework problem, which is at what velocity does the error between these two curves reach 1%? So if you're going slower than whatever that value is, then it's probably pretty good to use that formula for most cases. So here's an example. Suppose the Earth orbits the Sun at a speed. We know the orbital speed of the Earth is 29,800 meters per second. If you had aliens above looking down at the Earth, clocks on the Earth would appear to tick slightly slower due to the Earth's motion through space. So the question is how much time is quote unquote lost after one complete orbit after 1 year? And of course, this circular orbit is not an inertial reference frame. You'd really need to work out to use general relativity to get the precise answer, but we're going to ignore that for right now. We're just going to use special relativity and the velocity. So we're going to use this small velocity approximation. We want the difference in time between delta t and delta t naught, right? It's going to be a very small amount compared to a year. So we just want the difference. So we'll define this lowercase delta as the difference, the time delayed amount minus the proper time. Remember, delta t is just gamma delta t naught. That's the time dilation equation. You can factor out delta t. And then we're going to substitute in for gamma this quantity here, 1 plus 1/2 v squared over c squared. The ones will cancel out, and you get the delta, the difference between the times is just 1/2 v squared over c squared times delta t. So now you can plug in the values. We'll plug in for a year, we'll plug in the number of seconds in a year, which is about it's about 31 million seconds. Plug it in. We plug in the velocity of the Earth divided by the speed of light times the number of seconds in the year, and we get about 1/4 of a second, which is kind of interesting. So because of the velocity of the Earth as we're going around the sun, every year we're someone would see our clocks as running about 1/4 of a second slow compared to their own clocks if they were in an inertial reference frame that's in the rest frame, say, of the sun. There is a general relativity effect also, and that is actually I believe it's on the order of magnitude of the similar kind of value here, but we're not going to worry about that right now. Okay, so the next lecture is going to be about length contraction, so another result of special relativity.